Welcome to the last day of class. Oh, sad, happy at the same time. Yeah, so this is the last day of lecture. Thanks to the few, the brave, the proud that have stuck it out with me in person, keeping me company in here. And to those of you watching from home, thanks for watching. And it's been wonderful to see the view counts, climbing on YouTube. Usually right before the assignments are due, which is how I would do it probably, but Anyway, so yeah, it's been an interesting semester. Today we're going to do two different things. I'm going to follow up with the example that we were working on in class on Tuesday. I'm going to go ahead and kind of finish that up, and then I have a few slides to show you, and we'll see how far we get with that. It's possible. I did actually just finish writing the final exam, so if we have time, I could potentially squeeze in the final exam review. If not, I'll stick to my original plan and give out that stuff over the weekend over a video. So, any questions before I begin? I did get one question over email from a student who asked about the interaction assignment and asked sort of like, how much interaction do I need? I think one or two functions would be the kind of minimum. So if you're using maybe mouse pressed and mouse clicked, or maybe a mouse and a keyboard click, or mouse X coordinates and something else, just enough to basically make it interactive. Yeah, so that's basically it. It can be pretty much whatever you want, as long as it has some interaction built in. So getting to our sort of code example from last class, I made some very minimal changes to it. So I went ahead and I just got rid of the RGB sliders because I'm not really sure why I did that. I guess I just wanted to kind of simplify things so it can kind of be its own example. And so that just left this M slider. And then when I create the slider, I went ahead and I'll get into this a little bit later, what I did with create slider. The most important thing is that I took this code and I added this WebGL descriptor. We haven't looked at a lot of 3D examples in class. There are quite a few on the website and in my code collection. So you may notice that if you put this WebGL rendering context, if you list it after the dimensions of create canvas, then you get a 3D environment. It might not be immediately obvious that it's in 3D. You need to actually use some 3D objects like box or sphere, or you can even take a two-dimensional shape and rotate it around the X, Y, or Z axis, and it will appear to be three-dimensional. So in this case, we're using a box, and I wanted to go ahead and just have a static background, so I changed the background. And then also, this is still here. This is a really important component of the slider. This is basically what sends the data back from the slider to the variable called M, which is now a constant. So basically what's happening here is we've got our sort of, box object, which is really simple. When I created the slider, I did it a little bit differently than the color sliders. So the color sliders were set up like this. And that seems like a wonderful range of numbers to use for changing a color, right? Because you're going from 0, which is black, to 255, which is usually the white or the peak of the channel. So in this case, if I want to rotate this thing, I actually would like to do it as 2 pi. Now, this is not going to fully work. I'm going to show you kind of what the next step is, but let's pretend that we're just doing this right now. Okay? So we're going to make this rotation, this sort of number limit here of the slider, 2 pi. So let me run it and see what happens. Then also, just note quickly that here I'm using the rotate x function, and I'm rotating it by the value of m, which is what's being populated by the slider. So when I use the slider, it's sort of blocky. And there's a reason for that. It's because 2 pi is it's literally 2 times pi, so it's 6.28 whatever. I'm not one of those people that has pi memorized, much less 2 pi. But yeah, there's only 6 units here, so it looks like really jerky and kind of weird. I'm not a huge fan of that. I would like to have a nice, smooth interaction. So what I'm going to do to accomplish that is I'm going to go ahead and take 2 pi and multiply it by 10. And I'm doing that just so the slider works smoothly. The slider looks much more smooth, right? But now I'm rotating it by some crazy value, right? Instead of rotating it by a fraction of a revolution, I'm rotating it by like 10 times that. So here, as I rotate it, I can just divide it by 10, and it's going to smooth out that interaction. So here, now that I have it coming through and it's dividing it by 10, it's just kind of added more granularity to my slider. You could take that to the bank. So do I want to have it rotate in more than one direction? Well, that would be pretty cool. I mean, especially since it's 3D. I'll call this maybe N slider. So I'm going to enumerate another slider. I'm also going to turn off my chill out music there. Let's see, I also need to run these 2 lines of code again for N. So this is N, this is N. This can actually be exactly the same because we're just rotating it on a different axis. We're not changing the value, really, of the rotation, or what we would want the value range to be. And then down here, I could just maybe jog it down like 20 pixels in the position. And then I also need to fill it with a constant here. So then in here, I could basically just take this and rotate by y. Rotate x and rotate y are things that if you have not been looking at the 3D examples, you've probably never seen before. They are rotation methods that only apply to when you're working in WebGL. So now I've got this thing going here. Interesting. Might have a slight syntax. Okay, so that's my fault. I see the problem now. Basically, what I was doing here was I was applying m and n to only m slider value. So let me fix that. And right, now this one should rotate around the x-axis. So this is rotate x. And then rotate y will allow you to rotate around the y-axis. And you could kind of just position this as you will. So you should get full 3-dimensional positioning with those 2 little sliders. And so I just wanted to kind of close the loop on that from last class on Tuesday. I think we've looked at a lot of, simple interaction methods, and I want to kind of move on from that briefly to talk about some stuff that may be on the final exam. So we haven't sort of like stepped back to kind of look at code-based art much, so we're going to look at a little bit of that today. And one thing that we kind of want to maybe think about or look at is that as you go along in your daily lives after this class, and maybe you never look at code-based art again, or maybe you see it, just in advertising or, in your daily life, you'll notice some of these things, I think, as you kind of move through, your sort of, I would just say, everyday media consumption. You'll see these even used in special effects. So randomness is the first sort of like class of algorithm that I wanted to kind of give a little bit of extra attention to. So when we talk about randomness, it's not like, like if my cat just like walks into the room, while I'm watching TV and I'm like, oh, that's so random. That's not the kind of random that I'm talking about. It's literally like mathematical randomness, right? And how artists use mathematical randomness to sort of create visual information. It is important to note that actual pure mathematical randomness is a thing. It's not usually what most of these code languages implement, because it's actually really hard to get something that's truly random. So if we look at some samples, here's a short YouTube video. I'm not going to look at the sound, but it gives you a really good idea of what real randomness and what pseudo-randomness looks like. So as we cut, it's like a 1-minute video. So here's our sort of pseudo-random noise. And you can see when it's kind of zoomed in on, you can really quickly start to pick up on the fact that, oh, no, there's definitely a pattern in there. Like there's definitely things being repeated over and over again. And so anytime you look at, TV screen noise or that type of noise that you would see on a device, it's almost always generated. And so this is just sort of like a way to kind of illustrate the fact that even though it looks random, it is repeating and it is generated. It's kind of fun. Usually the fewer channels, so if it's black and white noise, it's obviously a little bit easier to see that pattern. Where if it's tricolor noise, it tends to kind of interrupt that a little bit. And here we get to the actual comparison. So anyway, we could watch that all day. But basically, like this is probably like a really crystal clear sort of illustration of what the difference would be. And the PHP random function is actually one of the simpler random functions. So you can see quite clearly, well, that's random-ish. It's random-ish. It's not actually random, right? So my sort of threshold for randomness, I mean, when you put them in these black and white bitmap configurations, you can really quickly and easily see how random they are. If you're making a ball like wiggle a little bit, you're never going to notice that it's not purely random. So it just depends on the context. I have never had a need for pure randomness. I don't work with sets that large, or it's just not necessary. So this is another way of thinking about randomness, and there's a couple of sketches in this folder over here, or in this document. So there's some sketches that correspond to these slides, if you want to kind of check them out. If you're using the advanced option for the second code assignment, you may want to look at any or all of these examples. These are all sort of chosen, directed from the prompt in the advanced option for the second assignment. So in any case, I'm not going to kind of like go through all of them, but I wanted to let you know that they're there. So random walk is a fun algorithm, and it's an algorithm that you can actually perform with everyday objects because it's so simple. It's something like go forward 2 steps, turn left, go forward 1 step, turn right, go forward 3 steps, turn left, go forward 2 steps. And that sort of flipping, that small number is just flipping around based on a random number generator. And you end up with something that looks like vaguely cloud-like. If you're ever super bored and you want to like entertain someone with the weirdest, most random in the colloquial sense thing ever, you can actually find these dancers from, I believe they're from Slovenia, and they perform algorithms as folk dance. I swear to God, on YouTube. It's a thing. So thinking about randomness is like one of the sort of like, obviously highly complicated if you're a computer science scientist. It's actually studying it. But for our purposes, randomness is actually, pretty simple. And how we implement it specifically in graphics is pretty simple. When we talk about noise, I usually skip directly from randomness to noise. And the reason is because, as you can see, this random result is kind of all over the place, right? Where with noise is basically a way of kind of creating controlled randomness. And the reason why noise is so prized is that it has these sort of ramps and smooth areas when it goes from point to point. With randomness, let me just go ahead and show you in here. No, not new. Sorry. Open. So I'm just opening this up for illustration purposes in a very related language called processing. So this is an example of what would happen if you wanted to have just random line heights, right? So it's using the random function, and it's saying every time you iterate through this for loop, pick a random number for the line height. And then contrast that, perhaps, with something like Perlin Noise. So with noise, this is what you get. And, one is extremely different from the other. I think we could say that for sure. Why would you want to use maybe randomness? A lot of people use randomness when they're maybe looking for something that has kind of a frenetic vibe. So if you're making like an animation and you want to have just like crazy lights blinking, randomness is great for that. If you want to have something that looks a little bit like chiller and a little bit more sort of like, modulated, most people will opt for Perlin Noise. And as far as the sort of like jaggedness of those peaks go, you can have it be very jagged or very shallow. So that's the other cool thing about Perlin Noise, is that it's scalable. But in any case, I use Perlin Noise a lot in my own work when I'm making animations and stuff like that. But it's the whole idea of Perlin Noise is really important to multiple types of computer graphics. So you can see here, this is what happens when Perlin Noise is used in a two-dimensional setting. So it's used here to sort of create areas of brightness and darkness. The place that you all have seen Perlin Noise for 100% sure is in 3D terrain generation for cinematic special effects. Yeah, if it's, not shot like on location in New Zealand, I know that the guys at Weta, when they made the whole Hobbit, Lord of the Rings trilogy, they did use dynamically generated terrain. And so Perlin Noise is also used a lot in flight simulators, anywhere where you have terrain that is sort of constantly being generated. It's usually just Perlin Noise that's sort of green. And then, of course, it also makes a great water simulator. And so there are plenty of artists that are sort of like foregrounding Perlin Noise as part of their kind of technical toolkit. This guy, Markus Watts, is a Norwegian-based code artist, and he is making these forms based on Perlin Noise distortions that he makes, and then he actually laser cuts them into these wooden panels. And they're really lovely. He makes really beautiful work. And this is Leonardo Salas. Let me get zoomed out here. Again, using Perlin Noise in a really beautiful and subtle way. His work has been featured a lot in some of the graphic design professional organizations. So that being said, one of the reasons I'm highlighting these algorithms in particular is that once you see them, it's kind of hard to unsee them, right? It's sort of like a filter in Photoshop, where kind of once you see it, you're just going to pull something up in your visual life and then just be like, oh, that, yeah. And so I don't know if that's a good or a bad thing, but it's definitely a thing. So the next one is recursion, and recursion is super fun. It's a method that is usually used to create or simulate natural forms. So things like leaves and leaf structures. Any kind of natural branching structure is usually going to be described with recursion. You can find examples of recursion on the P5 website. I'm not sure. Let me see if I put any in this advanced pile. Oh, no, I did. Yeah. So yeah, recursion is super fun. The sort of thing with recursion is that you actually have to have an endpoint. So in this case, it probably started here, and then it actually calls on itself, and then it goes until it sort of can't go anymore. Somewhat similar to a for loop, only it's structured a little bit differently. So here's some more recursion, tree recursion. This is a guy, John Powers. He was the only analog artist that was featured in this big digital biennale in Frankfurt a few years ago. And he literally makes algorithmically based art out of styrofoam blocks. So he's one of the conference organizers actually said that he's a machine that converts beer to styrofoam art. I don't know if that's true. I didn't get a chance to meet him, but I would imagine that there was probably some sort of multiple people involved in the creation of this thing. But I do think it's really kind of admirable and kind of awesome that he's doing something that most people would use, a computer, and actually just sort of creating it in reality. So he's kind of an interesting artist. And then this is just another example of recursion. Let me get it a little bit bigger on the screen. So yeah, this is a sort of two-dimensional recursion example. Recursion can be used to create terrain also. I've seen a lot of people create cityscape-like terrain with it, or also farming terrain where things are divided up in a certain way. And then you can also, this is another type of recursion. This is called circle packing. All of these sort of circle packing, any kind of algorithm that's listed in here, you definitely should be able to find it on the P5 website. Circle packing is fun. I think that there's quite a few people who sort of use it as a device to create their work. So here's a couple of examples of circle packing. And let me zoom in on this one a little bit. Maybe not that far. So that's an example of circle packing. And then, of course, this is an example of circle packing, which is, pretty close to a stippling technique that was actually used in engravings for real in the 18th century. And, with the right algorithm, you can kind of simulate that. So yeah, this sort of result and this result are sort of fundamentally based on the same type of algorithm that says, let's throw down all the big circles and then arrange around them slightly smaller circles, and then slightly smaller circles, and slightly smaller circles. So recursion's like a major sort of theme that you should be aware of as well. The last one I'm going to show is Varonoi. Varonoi is kind of somewhat misunderstood. A lot of people mistake it for the crackle filter in Photoshop, and there are certain implementations like this one that actually look like that. Varonoi is actually like a type of mathematical triangulation that takes a simple form and then divides it in different ways according to rays. So as far as algorithms go, it's probably the least sort of simple of all of these algorithms. It's probably been popular, I would say, in the last 10 years. A lot of people have kind of gone crazy using it. And you start to see people really take advantage of it in situations where they're trying to describe like cell biology, or this idea of, you know, things being somehow like divided, or also like almost like interstitial tissue, like spider webby type stuff. Kind of comes through there. I'm not going to show it in class, but this video by Ravenclock is absolutely incredible. It's generated in processing, which is the P5 sister language. Yeah, it has heavy use of recursion. And then this was actually the Adobe Artist of the Year a couple of years ago. And they actually have this elaborate process where they take illustrations, and they sort of take those illustrations, make them into Varonoi sort of, you know, you can see the Varonoi being applied here. And then they actually rework them with a tablet. So they kind of draw over it, basically, which is kind of an interesting technique, right? Because if you are using something where it's going straight from code to like a two-dimensional image surface, I mean, that's great. A lot of people do it that way. But, you know, you can kind of bring back this sort of like painterly effect, right? And so all of that gesture and all of that painting is actually just from working on a tablet on top of this digitally generated image. So it's a different way of kind of thinking about it, thinking about process. So yeah, I would definitely take some time to look at these. I think I'm going to go ahead and do the final exam review. We've got enough time. So I'm going to unplug my, that's probably not necessary. Yeah, sure, I'll unplug it. See what it does when it doesn't have my projector input. There we go. I'm going to go ahead and just set up the camera for a second here. So. Okay, I'm back. So let me open up the final. I've got it done already. So let's see. I'll preview it. First of all, before I sort of start talking about the questions, does anyone have any questions about the final in general that I should address? No? Okay. It is 20 points. I can't say it's 20 questions. It's got a couple of multi-part questions. But so I don't know how many questions it actually is. But it's 20 points. It's 20 small questions, for sure. So basically, most of what the final covers is the last 2 units that we've done. There is one area in which the final is cumulative. And it's basically, I'm going to tell you exactly what it is, because it's basically, if you didn't sort of catch this while taking this class, I have failed. It's that one thing. So there is a question on the exam that goes back to the first part of the semester. There is a question that asks you about the pixel size of an image. And so it shouldn't be a super challenging question for anybody, but if that doesn't sound familiar to you, if you're still wondering what a pixel size is, please do email me or a TA, and we will kind of, think about it and find out what your questions are. But there is a question about pixel size. So there, are some questions. Like the midterm, it's based on slides, and then also to a somewhat lesser extent based on in-class demonstrations. So there's a question about sort of like 3D modelers in general, which I'm pretty sure would come from the slides called Classes of 3D Modelers, NURBS versus Polygons. I would check that out. So I'm looking at another question that applies to that set of slides. There's a question about sort of the genre of art that we've talked about in class that is made with code. That specific genre, I'm not going to say what the slides are called because then I'll tell you what the answer is. So yeah, that. There's a question with, there's a couple of code questions. And I think I said this before, I actually put an entire P5 program inside the question, and then I block out a section of it and ask you a question about just a tiny section. So in pretty much all of those cases, the best way that you can ensure that your answer is correct is to just take that code and put it into the P5 editor and try out the answers that are listed. And if it works, then you've got the right answer. I guess if you know these things from off the top of your head, that's pretty impressive, and that might work too, but I would certainly want the extra insurance of checking them. So there's a question about sort of like one of the interaction functions and what it's called. And then, let's see, there's a question about the hierarchy of form in Rhino, which I believe I covered in the first Rhino demo. So what I mean by hierarchy of form, I'm not gonna sort of like list the hierarchy of form, but it's sort of like, this is the most fundamental element, this is the second most fundamental element, so on and so forth, up to something. And then a code question. So you do need to be able to identify the sections of a for loop, those sort of 3 sections. You need to know what a solid is in Rhino. There is a question, there's a couple of questions that have graphical images of Rhino sort of set up, and they ask you, what am I doing? Like something's happening on the screen, what's happening? So one of those questions has to do with like surface creation methods. So you may remember that surface creation method where we took a curve and then somethinged it around an axis. Yeah, there's a question about that. And then there's a question about another surface creation method where something is sort of, flat and then it gets less flat. What that is called. Let's see. And then getting into kind of P5 questions again. Let's see, what is it called? There's some questions about P5 that are based on kind of like practices. Like when I leave myself notes in the code, there's a question about what that is, what that's called. There's a pixel size question that requires you to download an image of my cat. and then tell me what pixel size it is. Let's see. There's a question about sort of the provenance of P5 and sort of what other programming language it is related to. Or maybe it might be more accurate to say what programming language is P5 a subset of. There are two questions about the setup and the draw function in P5 and like what each one of those things does. What is a variable? And there's a question from today. What type of algorithm is often used in the creation of 3D terrain in gaming and special effects? That's easy. And I have a question in here about sort of like, what are some of the what's the general process of creating imagery? So there's a question about rendering in general. There's a question about one of the artists from the Code in Art lecture, the sort of early on in the lecture. So that took me down to question 18, and I think that then plus the multi-part questions that that's the 20 questions for you. Anybody have any questions kind of moving on from that? Okay. I'm hoping, because some of the questions are short answer, I do actually manually grade those because, you know, I don't want somebody to not get points if they type like an extra character or something. So your grades will be automatically sort of generated, but I don't finalize them until I've looked them over because I want to make sure everybody gets the points that they deserve. So yeah, I mean, pretty much, so immediately after the final, you should be able to get your grade. Don't forget that we do have extra credit opportunities, which you can still take advantage of if you haven't sort of course, I'm not on the screen anymore, but the extra credit opportunities are at the top of the Canvas page for the class. And it says I'll take them until May 9th, but you know, our sort of drop dead deadline is the 12th. And if you really needed an extra credit point and you needed to turn it in on the 12th, that'd probably be just fine. So yeah. Anybody have any questions about the final or anything? Yeah. I'm pretty sure I just did that. Yeah. So I think I'll just like, you know, I'll send an email out to the crew and say, just look at the last half of this video. Yeah, because I mean, it was thorough. Just now, like I looked at every question. So okay, yeah. So I'll just for sure clarify that to those that are watching from home. I was just hoping that I would, you know, have some free time in class, and we did. So yeah, well, I'm not gonna keep you longer than I need to. Have a great summer and a great sort of like continued study here at UW-Madison. You all have been a wonderful presence twice a week. It's been great to see you, and it's been great to work with you and talk to many of you over email. Yeah, have a great summer. I'm pretty excited about it. Thanks.